Okay, good afternoon, folks. I want to welcome you to the webinar this afternoon on the Pheso Rheometer. Today's webinar is going to build on the first webinar that we did when we introduced the instrument back earlier this year. Today we're going to focus more on the design of the rheometer, how it compares to other types of devices on the market, and then go through some new applications that are above and beyond what we used in the first webinar. My name is Jeff Grow with Calmetrix. Online with me is Mark Zacharias of Calmetrix, who is going to do the presentation today. Just some logistics. We currently have everyone on mute. So as we go through the webinar, you can use the chat box if you've got questions. And then at the end, we can answer those questions. Before we open it up at the end, I'll also mention to you a promotion that we've got on the rheometer through the end of the year. So with that, I'll turn it over to Mark, and we'll get started. Mark?
Yes, very good. So good afternoon or good evening for those who are in a different time zone. So today is indeed about the Pheso Rheometer, and I want to structure this presentation in two different slices or pieces. The first one being about what is the design for a proper concrete rheometer, so that we can actually use it for concrete and the way it's supposed to be, to study the material that is so widely used in construction. And the second part is about a few practical examples. Once we design a concrete rheometer, what can we do with it that is sort of over and beyond what we could do today with the existing rheometers. And any good talk about rheology or workability starts with the most common tools that exist that we have all used in labs or in the field, and that is of course the slump cone and the ruler. And whoever wants to talk about the rheology or workability seriously has to have done at least a few of those slump cone tests and spread tests, mostly in the field, but of course also in labs. We've seen those in development labs. Everybody uses them, and for good reason. They're simple, they're cost effective, they're pretty foolproof, and they're very good. So it's normal and it's a good thing to use them day in, day out. However, for certain things, if you want to get serious about product development, about real optimization and cost savings, if you're an operator or a concrete producer, or if you want to help new admixtures, new ways to manufacture concrete, new ways to pump concrete, etc., you have to go a little bit beyond the slump cone and the spread test. You would look at things like mixing efficiency, like mix optimization, shearing cycles, exotropy, slump retention. Then you go into the science of workability, which is rheology itself. And then as you start looking for rheometers, what you will find in the market is a humongously large number of offers that you can get. You have many rheometers available, many more than for other types of instruments. However, what happens very often in the cement and concrete industry is that many lab instruments, I want to say almost all lab instruments, were developed originally for other industries. And although the concrete industry is one of the largest in the world, you will find that most instruments that you buy were actually not meant for this industry, or they were not designed specifically for it. They were adapted sometimes, and sometimes not even adapted for it. So the cement and concrete industry is very often the stepchild of lab instrumentation. And even things like the Hobart mixer that many, if not all, people have in their labs was originally not developed for cement and concrete. It was really developed for bread, as we know. And it has hardly been adapted very much to work for concrete mixtures or mortar mixtures. Now, as you look to the offerings that you have in the market, you will find that most of the rheometers that you see, the vast majority, were really built for homogeneous substances, such as polymers, oils, cosmetics, things that are a little bit pasty, quite fluid in general, and it's not so adapted for what we would want it to be in concrete. The concrete actually has different and unique challenges as a product. It's a granular suspension. You have a very wide particle size distribution. The particle size distribution in concrete covers 4 orders of magnitude, from microns to inches. And there's hardly any other substance that you could want to test that has the same range of particle size distribution. Not even asphalt would have that. You also have a wide range of viscosity. You go from roller compacted concrete or pervious concrete, zero slump concrete, all the way to self-consolidating concrete, which is almost fluid. And so this wide range, again, the rheometers that are out there were not designed for that. And you have large aggregate particles, inch-sized particles. So most of those paste rheometers, all of those paste rheometers that people use that were originally made for polymers and resins and oils and things of that type that are homogeneous fluids, all these are very ill adapted for the cement and concrete industry. Still, a lot of research centers, a lot of people buy those and make tests with paste and do a rheology or rheometry on paste. Yet, you may want to ask yourself if that's the right thing to do, because nothing in this world that I know of is really built with paste alone. So there's no walls of paste, bridges of paste, or buildings made of paste. It is made of concrete. So the right thing to do would indeed be to look at concrete itself. Now, case in point, we at Calmetrix, we are calorimeter manufacturers, and we like to put pretty much everything we see in a calorimeter and look at the hydration profile. As you know, if you know a little bit about calorimetry, calorimeters are very, very practical instrument, a very powerful instrument, because you have a continuous measurement of what's going on in hydration of your cement. And in this case, when you look at this curve that I show here, you will see three curves actually. You will see a paste curve, which is the green and yellow. So this is a paste with just a plain cement and an admixture. And then you would see the equivalent in water. So the same cement, same admixtures, but we added some fines to it, fine aggregates. And then you would see the same again in concrete, where we add the coarse aggregates to it. Again, same cement and same type of admixtures. When you do those three, you see very notable differences in the hydration profile, which tells you they have completely different setting times. They behave completely differently when you actually place them, use them. And the main reason for that is mixing energy. The mixing energy is very, very different between a paste, a mortar, and a concrete, because the particles, the friction, the movement of the particles in this granular suspension make for very different mixing energy between those three. And of course, we picked this example to be telling. So we picked it with an admixture that is known, with a type of admixture that is known to create those differences, which is a polycarboxylate admixture. And it is very, very common that with polycarboxylates, you would get completely different results between paste and concrete. So why then would we taste paste in the first place if it's not because, well, quite frankly, there's not much else available? Now, of course, a lot of you will say it's not true. There are concrete rheometers out there. Indeed, there are rheometers that were designed to be used for concrete. And notably, there's I can mention a few. There's the Rheocad, there's the Viscomat, there's the contact rheometers that come from Iceland that are designed by people that are very knowledgeable in rheology in general, and especially in the space of concrete. And there's the ICAR, like a field test rheometer. So all of those exist, and yet they also lack certain of the design characteristics that you would want to see in a concrete rheometer. So you can indeed test concrete in there and not paste. However, well, these suffer from something else. There's a problem called segregation, as we all know. Segregation of materials is when you have a mixture of fine particles and coarser particles of different sizes, different densities in suspension. And that is exactly what concrete is. And then one of two things very often happen. Either when your mixing movement is not right to create the turbulence so that those particles remain in suspension, they will segregate probably to the side. And if you let them without mixing for a while, the mixing method is not the right one, they will settle to the bottom. And once you have this segregation and you have a rheometer measuring the rheology of this substance, you will forcefully get a very wrong result, because what you will measure is not the rheology of the concrete itself. You will measure the rheology of one of the phases, either the coarser one or the finer one. And you will get results that are different from what it would be in concrete if all those materials were in suspension, properly mixed. So this means that with the traditional concrete rheometers that you have in the market today, the ones I mentioned, you would typically not be able to do, say, a long-term test. You would not be able really to get to the point where you can say, I would like to know how my concrete behaves from the very time I start putting in the materials and start mixing them dry, and then add the water, and then look how it mixes, and then over time check how the slump evolves, until placement practically. You could not do that. The only way you would do that is to take the concrete out of a mixer where you pre-mix, so the particles are nice and in suspension. Then you put them in the rheometer, you make a quick test of a couple of minutes, then you take the sample out, put it back in the mixer, and 10 minutes later you put it back in the rheometer, put it back in the mixer, back in the rheometer, and so on. It's very tedious and it's not continuous. So ideally we would want a rheometer where we can measure the rheology at the same time we keep the particles in suspension. So we want a rheometer that does not create segregation. So if we want, if you think about the ideal rheometer, the way we thought about it for concrete testing, well, it's not the paste rheometers that we talked about. In a way, it's also not the concrete rheometers that I mentioned, because they create segregation. We would want the following design attributes for rheometer. What we would want is, well, first of all, the ability for continuous mixing while we measure rheology. So we can avoid segregation and we can see continuously what happens while we mix, and as the concrete is in a state where it would normally be between the time it is batched and the time it is delivered to the site, or the time it is batched and the time it is put in the forms. We would like a high torque, because the existing concrete rheometers that you have in the market, the ones I mentioned, Viscomat, Rheocad, ICAR, et cetera, they generally, well, actually all of them, it's not generally, all of them need a slump of at least 100 millimeters or 4 inches slump. Below that, they cannot handle the concrete. The concrete is too viscous. Well, with a higher torque, you could very likely handle concrete that is all the way up down to 0 slump. Why not? Or dry materials, or roller compacted concrete. So a higher torque would not only give you this ability, would also give you realistic mixing energy. The same way, the ability to have a high shear rate or rotation would also give you a good mixing energy. You would also want this rheometer to have a larger bowl or vessel, so that you can accommodate for the large aggregate particles. They're part of the concrete, and you need to have a significant amount of those in there to have a substance that's representative of what a real batch is. And you need to build this device pretty solid, because if you think about it, if you have a large sample size, a relatively viscous liquid in there at times, and if you have those large particles, all this at the same time in a rotating apparatus, well, this will create significant amount of vibration, and you need to avoid the vibrations so that you have the right measurement and the right precision in the measurement. So we created this rheometer to exactly respond to those design criteria. We have a motor that is goes up to 147 Newton meter. This is high. This is very much higher than anything else that you find in the market, and this enables us to go down to 0 slump concrete, to do dry materials, to do all sorts of materials. We actually tested this with bread dough, which is not the driest of all materials, but it's certainly very plastic. And the plasticity of the bread dough is way more damaging to a gearbox or to a motor than even concrete could be, and it passes the test of the bread dough, which means that, in fact, for all types of concrete, there wouldn't be a problem. We, of course, tested it with 0 slump concrete, and everything works pretty well. We designed this rheometer with a planetary movement. Planetary movement is a sophisticated way of saying that your impeller is actually off axis. It rotates, but it's not around the central axis. And the shape of it is what we call an attritus shape. So it's designed to create turbulence, so proper mixing. The schematic to the right in this box shows you more or less how a particle on this impeller would move around. So it creates this turbulence that actually creates mixing action, and that mixing action avoids segregation altogether, and is realistically similar to what you would find in a real mixer. We have a 25-liter vessel. Actually, you could also have a choice. We have smaller vessels too. We have a 6-liter and a 25-liter. The 6-liter could be used for mortars or even paste. You can have small samples all the way down to 1 liter, and 25 liters typically for concrete. And don't get me wrong, on this rheometer, if you wanted to use traditional impellers such as the bobbin cylinder, the plate-on-plate, the vane, we also have those, and you could use those, of course, around the central axis, no problem. But as a real concrete rheometer for long-term studies, we would use this a Twitter impeller that is in a planetary movement. And of course, as we mentioned earlier, this has to be built as a heavy structure. And the structure overall of this rheometer weighs about 130 kilos, which, yes, is quite massive. It needs a couple of people to move it back and forth, at least. But in this case, it really helps us to keep the vibration low and get good precision in the measurements. So here's actually a video, and the video might be a little choppy depending on the internet connections, but I'm going to launch this. That shows how this planetary movement works. So, and what it does here, it starts slow because we're doing a shearing cycle in this particular example. So as you know, shearing cycles are made by letting the concrete rest for a while so that the thixotropy takes its effect, and it gets to settle. And after it's settled, you start little by little getting bigger and bigger shear rates, so more rotation, and you look at the behavior, the response and torque measurement to those shear rates. You can also appreciate here the size of the vessel when you compare it to the hand of the person that's holding it. So you see that it's there's ample good size to have large particles in there. So then the question comes up, of course, can Pheso really be used for long-term studies? Is this a commercial gimmick that we come up with, or is it something that we actually tested? Of course, we tested it. This is what you see here is, in fact, an example of a concrete mixture that is 94% cement, 6% of a fly ash, and then, of course, the aggregates in there, and 2 different admixtures. We're looking at the behavior over time as this would be continuously mixed. Imagine that this concrete is transported in a concrete truck, or that it's mixed. And we did this here for a total of just sort of 7,000 seconds, which is about more than an hour and a half, or an hour and 45 minutes. And as you see, we can actually, if you look at especially the blue curve, you can see that at some point we reached the setting time. You could actually see the setting time on this particular curve for this mixture. So you see the initial set. Of course, after a while you have to stop, because if you get to final set, then everything sets and it gets rock hard. It gets very difficult to get your impeller out and to save your vessel. So you see the initial set here on this blue curve. You also see actually what we didn't expect, but it popped up here, a false set, and the false set is very visible as this peak on the blue curve that you see that's highlighted and where you have an arrow on top. So it shows a stiffening, and then you mix through it, as happens with false sets, and you get back on track. So it's sensitive to see false sets, it's sensitive to see actually setting times, and you can indeed do long-term measurements without any issues on this, without ever taking the mix out to the sample out to remix it in an outside mixer. So you just go on and mix while you measure. The next question is, it's all very nice, we can indeed measure while we mix. However, how representative is this of the real world? Does it actually represent what really happens in a concrete mixer, in a full-size industrial concrete mixer? And we tested that too. So what we did, we took a 2 cubic meter size concrete mixer, which we consider to be industrial size, so it's rather large, and we retrofitted it with a torque measurement device. So we could measure the torque on this large industrial mixer and compare it to what we would get with the same concrete mixture in our own Pheso rheometer. And what we got is, here you see those 2 curves. So you see the green one. If you follow the green one, this is the one in our rheometer. And if you see the orange one, that's the one that you get in an industrial mixer. And what interests us is to see that how can you compare the behavior? Does it correlate or not? So indeed, now as you first put in the materials, you get those bumps as you put in the dry materials and then some other materials, and then after a while you actually you put in water, and then you see that the water creates another bump, and then as it mixes, you slowly but surely get to the state where you have a certain fluidity and where you get to a stable suspension of your particles in the concrete paste, in the concrete. And as you can see here, the correlation between the two is next to perfect. Now, of course, when you look at the green curve, you will see that there's more detail in there. That's because the rheometer is more sensitive. So you see more things that you would not typically see on the torque measurement in the larger mixer. But overall, the shape of the curve, the behaviors are the same. So this means that what you see in our rheometer is indeed very, very representative or highly correlated to what you will see in a real mixer. Therefore, if you do a long-term testing in the rheometer, you would get a very good idea of what happens in a real concrete truck or in a real mixer in the field. And the applications of that are numerous, and we'll get into some of them a little later. But if I'm an admixture developing company, or if I am a concrete company, I want to understand my slump retention over time while it's in the truck, this is ideal. Right? So it's a tool that is easy to implement, and it's very telling, and you can use it in a controlled environment, which makes it very, very attractive. Now that we have a rheometer that's designed for concrete, so a rheometer where you can use real concrete, not just paste, a rheometer that doesn't have segregation, a rheometer that can be used for any concrete from zero slump all the way to self-compacting concrete. Now that we have this, what are the things that we can do with it? So we can think about a number of applications, and I'm sure there's more. But for example, you could think about, as I mentioned just now, looking at slump retention from initial mix all the way to placement. So if I want to try different slump retaining admixtures, the SRAs, or if I'm an admixture company that wants to develop those, I would use the rheometer to look at the effectiveness of those. I would be able to compare them. I would be able to look at different dosages, and I would be able to look at the effect of different mixing methods, different speeds of mixing, different mixing energy, the effect that this would have on my slump retention. We could look at the proper sequence of materials when we make a mix, when we first mix ingredients together. For example, if you have a concrete that has fibers, you might ask yourself the question, so what is better? What is more effective and gives me a better workability? Is it if I put the dry materials in to the mixer, then I add the water, and then I mix, and after a while I add the fibers? Or is it by adding everything, all the dry materials and the fibers up front, and then the water, and I mix them all together from the beginning? It's not the same, it's different, and it gives you different results, and you can study that, and we actually did. This particular case study exists, so we did study that in the Pheso rheometer, and it gives you answers about this. You could look at selection of admixtures for more efficient mixing, faster mixing. When is that important? It's important when you have, for example, continuous systems where you have a mixer conveyor where materials get mixed at the same time. They get conveyed in a screw conveyor type to a site where they're placed in a form or used for something else. So this mixing has to occur very rapidly during transit in this conveyor system. And here you would want to look at admixtures that are best suited for that. There's also a case study that we have in our library if someone is interested. You could look at pumpability. Try different viscosity modifying admixtures and see what their effect is, and see if it's more cost effective or better to use a VMA at a higher dosage rate maybe, or to just increase the paste. As you know, pumpability is an issue in many instances where you have well, of course, when you have a high rise, for example, because you would use concrete that is typically very high strength, and it has a low water cement ratio, so it is more viscous, it's stiffer, and it's a problem for pumpability. So you need to help with admixtures, or you need to help with other means, but it's not just adding water, because that will ruin your strength. So here you could study all this. You could look at choice of aggregate gradation, so having different particle size distribution of aggregates, different gradation of aggregates, coupled with different air entraining agents, will give you a very different rheology. And you could look at this here again easily and continuously, because you mix your materials in that bowl, you put them directly in there, you don't have to have a separate mixer, you put them into the bowl, the vessel of our rheometer, and then you start mixing and measure at the same time. And both aggregate gradation and air entrainment have a very, very large impact on rheology, on workability of concrete, and testing both together makes for complex test matrix. Doing this with your slump cone and your spread testing ruler, or doing this with the other rheometers that you have in the market, would be a nightmarish endeavor. With the Pheso, it's relatively straightforward. You could select superplasticizers for self-consolidating concrete. It's very common. You make your flow tests, you look at thixotropy, and you make sure that you minimize segregation. This is very standard, and this is not really something that only Pheso can do. That other rheometers can do this too, but again, here it's made easy. You can detect the set or the false set, but not that this would be a very common application, but it's doable. You could, as I said, measure rheology of very dry concrete, pervious concrete. All this would work. But of all of those that we have listed here, I actually want to talk about another one that is pretty practical, a little bit more mundane, not as fancy, but we're going to look today at an example where you see how to optimize a mixing process, how to make the mixing most efficient. We will look at different variables that you can touch and that have a certain effect on how efficient the mixing is when you mix your concrete initially in your concrete mixer, whether that is in a precast pre-stress operation, whether this is in a ready-mix concrete environment, or even in a small mixer where you end up doing things by hand, one of those small lab mixers. So it has validity and to study those different variables. So as we know, rheology is sensitive to a number of parameters. The material selections, which aggregates you choose, which cement you choose, the admixture types and dosages. There's countless brands and different types of admixtures, and you have lots of products available. And the dosages that are recommended vary widely depending on your cement content, on your cement type, on what other types of admixtures you might use in conjunction with say, a water reducer. About SCM, so supplementary materials that you might use, all this has an influence. Mixing time has an influence, and it's one of the parameters that we'll look at today. So how long do you mix? Again, when you have one of those systems where you mix at the same time you convey, it's very important to know that if you're conveying of the materials from the start of your conveyor, screw conveyor, to the end where it gets dropped into a form, is less than a minute, then you got to make sure that in less than a minute it's mixed and homogeneously mixed. So you could look at this. The time of addition of water or admixtures is important, and finally, of course, the mixing energy, the shear rate. So why is this something that we may want to look at? Well, I think it's practical because this is something that normally concrete producers would be interested in. They would be interested in having more efficient mixing because they will get a better product. They will get a cheaper product. So it's cost savings, better quality. Who wouldn't want that? So I think the more sophisticated ready-mix producers would naturally try to measure things so that they understand their quality better. They can modify so that they can get a better cost. So especially in tough years, we all know the ready-mix industry works on a low margin when things get tough, and it gets important to optimize your materials, optimize your processes. Concrete admixture suppliers would also be interested in this kind of thing. When they would develop admixtures, they want to understand completely the effect that it has on mixing. They want to make those admixtures robust so that they work across the board, and they want to be able to recommend to their customers what the best mixing type is or the mixing procedure is so that the admixtures are used more effectively. And as we saw earlier, admixtures are very sensitive to mixing energy. So the mixing procedure is very important when you use admixtures. And everybody uses admixtures, of course. So academic researchers also would look into this, because when you develop new materials, new methods, let's say new sustainable materials, there's a lot of new sustainable materials now, it's important to understand the impact that those materials have on the rheology. And having a rheometer like Pheso, where you can put your materials in the vessel, you mix them right there, you can continuously see over a period of time how the continuous mixing that you would have in a ready-mix truck affects your workability, your rheology with those materials. You learn a lot, so you get a significant advantage, and you're able to develop things a little quicker. Now, all these things, a slump cone and a ruler, definitely are not enough to do this. So you could engage into a large endeavor of using a slump cone and a ruler, but it would mean many samples, many man hours, a very tedious effort. You could not do all this eventually with a paste rheometer, and you cannot do this properly with a rheometer where materials segregate or where you cannot use put a proper mixing energy that's representative of the real world. So Pheso would be really an ideal rheometer to do this kind of case study that we present here. So we looked at different things. So the first thing we looked at, and that I want to show you, is the mixing time. So if I mix for 17 seconds or 47, 87, or 297, or how does this affect what I see in my concrete, and how does this affect whether I see a stable suspension or not? And you would define a stable suspension when you look at this curve here. When this curve levels off at some point, and eyeballing it is very often difficult when you try to find the exact point, but you would look at the first derivative, and that would give you an indication of where that point is. So when it reaches what we call the point of fluidity. So this point is where you get a stable suspension of the materials, and the material becomes fluid and pretty stable after the mixing. So this type of curve tells you how long you would have to mix to reach that plateau. And very often you would use dispersants to help with that. Disperse the materials quicker in the mixture, and this better dispersion helps you to get a stable mixture quicker. So in this case, we indeed looked at different mixing times. Is it enough to do 17 seconds, 47, 87 seconds, or 297? And we looked at the case with and without a dispersant. For all of those, we used the same water addition ratio, so we were adding the water at the same flow. We use the same mixing velocity. So what you get with the rheometer, we did two sets of tests. So the curves that you see on top are without the dispersant. And first we did, this is the curve you see here, we just did the mixing efficiency test, where you essentially just look over time. So this is a time axis. So over time, you look at the torque, which is equivalent to shear stress. You look how it evolves, and when it essentially becomes more or less flat, right? And what you see in this case, well, quite frankly, for this mixture, 17 seconds is not enough. That's the blue curve that's hidden here behind. 47 seconds would not be enough. That's the orange here. 87 would not be enough to reach stability. 297 seconds of mixing, yes, does reach stability. When you look at the same with the dispersant, well, you'd see that, in fact, well, same conclusion. 17 seconds are not enough. 47 are not enough. 87, actually, you get there. 87, you're not far from reaching stability. And 297, of course, again, you reach stability. And what you can also observe is that overall, with the dispersant, unsurprisingly, you get to a flat state, or ultimately flat state before in time as compared to the upper curve where you don't have a dispersant. So the dispersant indeed works in this case, and you wouldn't stop here, or else I can show you more and more and more of this. But the principle is the same for all. What you would do, you would, of course, the next step, you would compare two dispersants, and then you would compare dosages, and then you would make an educated decision on which dispersant to use based on its cost, on how easy it is to get, how easy it is to use, and other criteria. But it helps you get and make a very educated decision on what the best dispersant is. And the best dispersant might not be the best for all of your concrete mixture. It depends on what else is in that mixture. And as you know, the interaction between materials is really what guides the performance of those mixtures. Very often the materials standalone look very good, but when you mix them together, there's some interactions, and those interactions, you cannot really understand them unless you make a continuous measurement of what happens during mixing. And on the right-hand side, we did those flow curve tests, so those shearing cycles that I mentioned earlier. So what we would do in this, if I take, for example, the blue curve here on top, and this blue curve is the mix that was mixed for 17 seconds. So what we did, so we mixed for 17 seconds, and then we let this mix stand, because that's what you do when you do a flow curve test. You let it stand there for a while, so that the material settle and goes back to what its initial state would be before the mixing. So after it's settled for a while, you take it and in the rheometer, so it's still in the rheometer, you would ramp up the rotation speed little by little. So, and you make a measurement point, so several measurement points as you ramp up, and you ramp it up, and you're up and up and up, and you measure the torque at the same time until you get to a speed of about 300 RPM. And as you're there at 300 RPM, you go back down. You go back to 250, 200, 125, etc., and you measure the torque. And with a mixture that was properly mixed and behaves the way you want it to behave, these two curves would normally overlap. The path going up in rotation speed and the path going down, you'd want them to overlap. And what these flow curve tests here show, they essentially confirm what we knew from the other curves here, is that the blue curve, which was mixed for 17 seconds before we did the flow test, this mixing is very incomplete, badly mixed. It's a bad concrete behavior. So if this was concrete that was in my famed screw conveyor that I mentioned so a few times already, where you would mix at the same time you convey, this would not give you a very good result. You would get concrete that is likely segregated and of poor quality at the end of your conveyor. Of course, we see what we also expect from the other curve. We see that the 47-second mixing, the orange curve, is hardly better, that the green barely gets there, and that at 297-second mixing, we get a concrete mixture that's quite decent. All right. With the dispersant, we would see similar conclusions, except that, well, we get better results because the dispersant in and by itself gives you better results. They're globally better. They're all a little closer in the path. There's closer to overlap, and the ones that overlap even better. So it confirms again what we've seen. Of course, when you see the curves like this, it may seem pretty trivial. Yes, we all know that dispersants are indeed better, are indeed a good way or a better way to get to proper mixing more quickly. But as I said earlier, the proof of this, what you would do is you would look at several dispersants and compare them to one another. And that would give you actually more information than just comparing not a without dispersant or with dispersant. So it's a useful tool to pick your admixtures and to pick the right way of mixing. Now, here we've been looking just at the number of seconds, the time you're mixing through your mixture before you get to stability. But something else we can look at is, in fact, the water addition rate, how quickly we add the water. So in this case here again, we made 4 different samples. The first one, we added the water at a rate of 8 grams per second. So it takes a little longer to put all the water in the mixture. So it's the same water cement ratio, except that we add it slower as we mix. So we start mixing and we have a relatively slow flow of 8 grams per second, and that's the green curve. Right? And when you add the water quite slowly, well, it takes a longer time to actually mix. So you see that the torque goes up, and then it goes down slowly, and it reaches stability after a certain point. As you go up in the rate of addition of water from 8 to 16 grams per second, then to 46 and 128, more and more you see that the stability is reached a little earlier, and that the mixing is actually better. So in this case, without a dispersant, we would recommend for this mixture that you go all in and add the water pretty quickly up front before you start mixing. With the dispersant, again, as expected, overall, these are all better. Actually, what we see here, I'm not sure I can explain why, but with this dispersant, it seems to be that the water addition rate of 46 grams per second is the best option that you have. It reaches stability the quickest, quicker than the one where you add water in a higher flow rate at 128 grams per second. You see the red is 128, the blue is 46. So in this case, the 46 grams per second would be the winner, so to speak. And just like I mentioned with when we looked at the total time of mixing, in this case, you would want to try different dispersants or maybe different speeds of mixing as well, and see what influence they have on this. At the same time, you vary the water addition rate, and you could select your best admixture and have the most efficient mixing. So something else a little more complex, it looks more complex, but it really isn't, that you can do. You can vary the shear rate or velocity, the rotational speed of the rheometer, and you can see at what rotational speed, what type of mixing is the most efficient. So how vigorous does it have to be so that you reach your goal? Say, for example, that you really want your mix now out of the door in less than a couple of minutes, less than 120 seconds, it has to be done. For whatever reason that is, or it has to be in the form, your mix that has to go right in the form. So you would look at the right shear rate, the right rotation speed for you to reach that goal. So you can do several tests at different rotation speeds in the rheometer. So you put in your sample, you would measure the torque maybe at 50 RPM, and you would do this again with another sample at 100 RPM, 150, 200. You get a few curves like that. And as you get those curves, well, you can have the software trace this kind of 3D thing. So the 3D thing, as I said, looks more complicated than what it is, this in its shape. But the software would, of course, help you find the optimum of your rotational speed so that you have the best mixing in the time you want. But yet another criteria that you can look at. It can go on and on and on, because we can look at admixture addition time, we can look at admixture dosage, admixture type, all these different things. And of course, when you do a study for yourself, you do not have to do all parameters. You know which ones are important to you and which ones you have control over. So it's a choice of the user to see which ones you study. So here we chose to look at something that's a little more esoteric. We said, well, why don't we look at this mix with two types of aggregates? So we could have the same mix, same exact mix, with aggregates that are a little rounder in shape. As you see here, the blue ones are a little rounder in shape. So they were selected to be rounder in shape. They were selected to be similar composition, similar everything, similar density, similar particle size distribution, but they had a different sphericity. This was actually a quite extensive study that was done, somewhat complicated. And so we would be able to look at the same mixture with overall aggregates that are very comparable, but on one side you would have those that are a little more spherical, as you see in the blue one here, and then you had the other ones that are of more lamellar shape, which are the orange ones. Now, in the real world, of course, concrete producers will laugh me out of the room, and they will say, I have no choice on spherical or lamellar aggregates. I cannot go to my aggregate producer and say, I want them spherical. They don't know what I mean. But it's not what it's meant to do. It's not meant so that concrete producers can go to the aggregates suppliers and ask for a different type of shape of aggregates. That's not really the purpose. The purpose of looking at this is, when you have issues, is understanding where those issues could come from. So when you see that your aggregates overall are a little bit more lamellar, well, this seems to be the case, that you use more mixing energy and more torque. So with certain aggregates that you use, you might actually see that the mixing is very thorough, it works very well. And then as you use those that are a little bit more lamellar from this source, you will find that you have trouble getting to the same performance, even if you use the exact same mixing protocol. So what would you do? Now, you do not go back to your aggregate supplier and say that you want a different shape. You now try to correct for it, because now you understand that there was a problem. So you could go and find an admixture that helps you with that. You could go and maybe have a different shear rate, a different speed of mixing for this kind of aggregate. You could maybe adapt something else in your mix, add a little bit of paste for this type of aggregate so that you can compensate for it and you can get the same quality. So this is not about unrealistically going back to your supply and asking for something it cannot deliver to you. It's about understanding the issue with the rheometer and being able to compensate for it. As we all know, the first part of solving a problem is understanding where it comes from. So when you measure it, you're able to tell. So this shows you an overview on this example. We have many other examples. So if you're interested, contact us. The ones I mentioned before, the sequence of addition of materials versus the fibers, looking at the best admixtures for self-consolidating concrete mix, pretty standard. Looking at slump retention, looking at pumpability using viscosity modifying agents. We have a lot of those examples in the library. So if there's anything you're interested in particular, just contact us and we'll be happy to oblige. But the overall takeaway from this is that once you have a true concrete rheometer that provides you with the ability to do continuous measurement, long-term measurement, no segregation, using real concrete and all types of concrete, well, you can do pretty powerful things in your lab. And knowing that the rheometer is so well correlated to real world mixers and real world experience too, is something that is it makes it very easy to solve problems and do your QC. So it's of high value, I think, to pretty much any lab, whether it's in development, in quality control, or pure research. And because I've been talking about some other rheometers that are in the market, we actually have a small comparative table. And here, I want to say somewhat arbitrarily, I picked a few. One of them is a pure paste rheometer, the one from Anton Paar. And I would say he's representative of what other paste rheometers are. Pretty similar in terms of performance and what it can do and what it can't. And then the other ones, the other three, are some commonly seen rheometers that are sold as concrete rheometers. And we're not going to go through this entire table because that would be a lot to look at. And for sure, you can get this presentation after we're done here, and you can also get a copy to the webinar with the whole webinar as a video. But I want to just look at 4 or 5 of those attributes that Pheso has and that make it different. So if you look at the arrow on the top, it's the ability to make long-term tests. Well, no other rheometer can do the long-term tests. As I said, you would have to carry your sample back to the mixer, mix it for a while, then carry it back to rheometer, and then back to the mixer. It's so tedious that no one really is doing this. And then rotation speed is actually faster than other rheometers. We go up all the way up to 550 RPM. And here again, it's because we want to be able to impart the mixing energy that is realistic and that is as close as possible to what you could get in the real world. When this is what it takes, we need to be able to push the limits. And it's the same for torque, or maximum torque is much higher than what you see in the other rheometers. The 147 is much higher than what you see with the others. Then we have here the ability to do any slump of concrete, so no other rheometer can do that. All have a requirement for at least 4 inches slump, or millimeters, and we can do actually fiber suspensions, which the other rheometers can also do, hard fluids, etc. So, to summarize really what Pheso is, and that is different from others, well, Pheso is actually a true concrete rheometer because it can measure concrete in all its forms and shapes, and it can measure it just continuously. And other concrete rheometers, they work in certain circumstances, but not always. So when you have concrete that is lower than 4 inches slump, they have to recur to mathematical models to try to find mathematically what the results would be. It's no longer measurement. Now, the measurement only occurs above 4 inches slump. So we truly believe that we have something that was designed for the cement and concrete industry, and that this time it is something that from the grounds up was meant to be designed for the cement and concrete industry. And with that, I want to leave it up to questions, of course.
All right, thanks a lot, Mark. I hope all of you share our excitement about this instrument, and Mark went through very effectively why this is so different than the other options that are out there in the market today. So if you've got questions, use the chat box, and we will answer those questions. In the meantime, I'll mention a couple other things. Mark mentioned we will be sending out for everyone that registered. You will get links to a copy of the PDF of the slides, as well as a recording for the webinar. So those will be sent out in the next couple days. And the other thing I'll mention is the Pheso rheometer typically costs around 69, or I'm sorry, it's about 67,000 typically, with the 25-liter bowl and the attritor mixer. But through the end of the year, we do have a promotion running that you can buy that system for about 48,000. So about a 30% discount for orders before the end of the year. In addition, we're also actively seeking out laboratories where we might collaborate in the sense that you could buy the rheometer for an additional discount in exchange for access to your lab. So if you're interested in pursuing that, then certainly you can get in touch with me. So with that, I want to thank Mark for the presentation, and we will stay online here. If you've got questions, please use the chat box. Let's see, there is a question here, Mark, from Bruce. How does this work on a construction site?
Actually, it works quite well. One of the design criteria we had, this was developed initially because there's a company that wanted to use this on dams that they're building, and they wanted to have it on site. So there's several iterations, several generations of this product, and I must say the first ones corroded pretty badly. It was used on a dam, the first dam, it was used in the Amazon forest, which is humid, and after a year and a half, it corroded all the way. So there have been iterations of that, and so the last iteration has been there for what, 6 years, 7 years, and there's no sign of corrosion. And so you can take this to the field. The way it will be done is pretty heavy, so you have to transport it there, of course. But the way it's done, you put it in a tent, and you leave it there, and you need a little base for it. It works very good. Of course, you need electrical supply, but it works very, very well in the field. It can stay here for extended periods of time. I don't want to say it's very practical moving it because it's so heavy, but it's not complicated to put apart and put back together. So there's no complicated calibration either because it self-calibrates. So you just set it up and you make sure it's protected from the elements as much as you can.
Great. Good question, Bruce. That would not have been a question that I would have thought of, but that's great. Yeah, it is definitely not a portable unit. It's not something where you could, on a routine basis, move it from location to location because of the weight. But as Mark,
I wouldn't take it to customers. I wouldn't take it to customers for a demo. So some customers ask for a demo, and so we cannot really. It's difficult to carry this around and set it up on your table in the conference room and show you how it works. But which is why we offer this discount to demo sites, because if we have demo sites where we have gentle access to, which doesn't mean we're there all the time, but then occasionally if a customer wants a demo, we would take them along and show this at your site if you become a demo site. It's the reason for us doing this.
Okay, do we have some other questions? We'll Mark and I will stay online here for as long as folks are here. Here's another question, Mark, from Zoran. Hope I pronounced that correctly. If I need a slump of 100 millimeters, what is the corresponding torque approximately?
Well, you would calibrate this when you have the equipment, because the torque and the slump are not just related like this. There's no universal correlation between torque and slump that you could use. Otherwise, it would be very easy. But you might be familiar, actually. There's some rheometers on the truck, the Verify system, right? So the Verify system is something that measures the slump continuously in your truck while it's in transit. And it's a fine system, and it took very many years actually to establish on this system to establish the algorithm that enables constant calibration of slump versus torque. So it depends on many factors. So while there is a correlation for any given mix between slump and torque, it is not universal. So it's not a straight answer. You would have to put your mix in together and establish this correlation, and then once you have it, you can use it.
Yeah, I'm assuming, Mark, that would be a function of the mix design. That correlation.
That's right. So
right.
That's right. The mix design, of course, the type of impeller you use. As I said, we have the attritor impeller, but you could use other impellers. The size of the vessel, the size of the mix, there's different, and in fact, it also depends on your shear rate. So, but if you keep everything else constant, then you can make a correlation, and you could use this as an approximate slump meter. If it's for slump only, Zoran, I still think that a good old slump cone. I would love to sell you something that is several tens of thousands of dollars. But if it's just slump, a good old slump cone is just doing the trick still.
Zoran, hopefully that answered your question. We have one other question from Wei Hu. How do you determine the yield stress and viscosity of the mixture?
Okay, so that's a very good question, because here you see you have a trade-off. It's interesting because usually it is widely accepted that you use the Bingham model when you look at concrete rheology, and the Bingham model works for certain geometries of the impellers and of the vessels. So you would typically you have a Bingham model, you have a plate geometry works with the Bingham model, a cylinder, so a bob in a cylinder works with the Bingham model. A vane actually would work with the Bingham model as well. And as you do that, you can correlate your shear stress and shear rate with the torque and with the rotation speed. And when you correlate that, you get to viscosity measurements and and yield stress and all those things. So as in the proper units and values. Now, when you use those geometries that work with the Bingham model, they have they have a tendency of not mixing well, so they segregate. So here's what you do with the Pheso Rheometer. If you need a measurement of viscosity and of yield stress, you can very well put those traditional geometries of impellers. We sell those, so you can get from us a normal quote unquote impeller that is, for example, a plate and plate, and you install this on the central axis, and you use our normal vessel that we have there. It's like a cylinder vessel, and then you use the same equations and you get your results. But in terms of doing continuous mixing, no, you can't, because if you do continuous mixing and continuous measurements and want viscosity continuously, well, it won't work, because here you have your trade-off, you have your dilemma. If you use your traditional impeller shapes, you can use the Bingham equation, but you don't mix well, so the concrete will segregate. So whatever values you get are junk, right? But if you have a Tritter impeller, well, there's no model, no mathematical model, unless someone wants to start working on it. There is not, as of today, a mathematical model that correlates the two. And you'd be hard pressed, because all those models actually assume a laminar flow. And that alone is contrary to what you want when you mix. When you mix, you want turbulence. So I want to say that, to me, it seems incompatible, which means, in summary, you have to make a choice. When you want to measure hard values of yield stress and viscosity, use the traditional impellers, but you can't do long-term testing, and then switch back to a Twitter when you want to do long-term testing.
Yeah, just to follow up on that. So the bottom line is the Rheometer is available with 4 different types of geometries. We have a plate geometry, we have a cup and bob type of geometry, and those, because they can be mathematically modeled, then you can basically plot shear stress versus shear rate and get the viscosity and model it, and so on and so forth. And then we've got a standard vane and the attritter, which typically, when we use those, and all the data that Mark presented in this webinar use the attritter type impeller, because it can't be mathematically modeled. Then the y-axis is torque, and the x-axis is speed. So it's qualitative in that sense. But the beauty about the instrument is that you can actually, within the same test, mix using the attritter, and then if you need a measurement at that particular time, quantitatively in terms of shear stress and shear rate, then you can pull the attritter out, attritter mixer impeller out, put on a different geometry, drop it into the sample container, and so on and so forth. So there's a lot of flexibility there, but there is that basic trade-off that Mark explained. Okay, other questions? One thing I'll mention while we are waiting for other questions, back on the weight of the instrument, and the need for the stiffness of the instrument. It's not only related to vibrations, but it also is, you need a stiff instrument so that as you make these measurements at high torque, the instrument is not moving because of the high torques that we have to use, for very stiff type materials. So it's important that all of the torque goes into the sample and the measurement rather than bending the instrument itself. So that's another reason why it has to be so heavy and so stiff. From Bruce, did you observe a significant difference between the traditional slump test and the Pheso results?
No, actually no. Once you have correlated your slump results to what you would get in the Rheometer, the correlation is very good. So you get results that are very predictable. So looking at your rheology curve, you can predict the slump pretty nicely. But as I said earlier, the Rheometer shouldn't be used just as a slump meter. It would be a waste of resources, waste of money. For slump meter, you still have the slump cone. It works very well. It should be used for more than that.
So let's see. We've got a question here from Tom at GRT. Mark, any applications using a really stiff mix design, something like a roller compacted concrete?
Well, we've tried zero-inch slump, but no, we haven't tried roller compacted as such. So I want to think this works because we went pretty extreme. In fact, the reason I know we went pretty extreme is that in the initial phases of design, when we went extreme, we broke the gearbox, and then we redesigned the gearbox and did it again, and now there's no issues. So that's why we all remember at our lab that we went extreme. But I will ask specifically the people that designed this for the roller compactor because it's, I want to know if we really tested this as such. So I owe you a definitive answer on that.
Okay, Tom, I'll get back to you on that. Just make a note and we'll let you know. Mark, one other question here. This is from Joshua. Does the planetary movement eliminate/minimize plug flow?
Yes, it actually, so the planetary movement combined with the shape of the impeller minimizes what is called plug flow. It minimizes any type of agglomeration of particles. It is as efficient as a normal mixer would be. So the correlation between the mixing is not only on what you measure, between the mixing in the Pheso Rheometer and what you see in an industrial size mixer, you would typically have the same behavior. Because this attritor impeller is very similar to what you would see in mixing devices.
One comment again, Mark, from Tom. GRT, love the fact that mixes won't segregate, but it would be great to segregate mix on purpose, add a VMA, and look at the recovery of cohesion in order to evaluate the efficiency of VMA.
Ah, that's right. Actually, yes, we have done similar tests as well. You can do that in the Rheometer because you can start with another type of impeller. I showed you the attritor impeller because that's the one that makes this real true concrete Rheometer. But we have the normal shapes of impellers that are traditionally used, the cylinders, the plate, and any other type of impeller or that are not efficient for mixing. So you could indeed put this in the central axis. You don't have to use it in planetary mode, by the way. You can very well use it on the central axis. You can mount the impeller both on the central axis and on the planetary axis. And then you would mount another type of impeller in the beginning. You would measure your rheology and see how it segregates and say, oh gosh, it's segregated. And then you can interchange the impeller, which is very quick because we have a mechanism that you basically with one hand, you loosen the ball. It's very easy to move. You'd have to have the Rheometer on the floor because the ball is heavy. And then it's a quick quarter turn unscrewing to get the impeller out and change it. So you could start with an impeller that makes it segregate and then change and look at the recovery indeed. So the test can be done. I agree, it's a nice test to do.
Yeah, I mean the one really nice thing about this system, Tom, and for the others online, is the flexibility that you've got. I mean, we didn't go through it here, but you know, there are two different mixing bowls, a 25 liter and the 1 liter bowl, and there are 4 different types of geometries basically. So Mark, as Mark indicated, the one that's probably going to be used in most cases will be the attritor with the planetary motion, but there's also a vein geometry as well as a plate geometry and a cup and bob type of geometry. So, you know, you got a lot of flexibility, and you know, can change those geometries in the middle of the run, so to speak, and as Mark alluded to. So hopefully that.
Actually, if you wanted to use this like the other Rheometers, the ones that I spent 30 minutes bad mouthing and saying that they're not good, you could also use our Rheometer that way. You could take the small vessel that could be used for paste or mortar, and you could take a normal bob and cylinder and put this in the central axis, and then you could emulate the results. So, for example, if you have an existing Rheometer that operates, so let's say with a vane, for example, on the central axis, you could replicate those results in our Rheometer, and you could get a comparison with what you had before. So you can definitely use ours in the more traditional way, the one that I said we shouldn't use it, but it's possible. The design makes it possible. The person that signed up as user says, I conducted a rheometer test on cement blended with an agricultural waste ash. What I found was that the mix became stiff. If I have two mixes with different water content but with the same flow, can these mixes be used as samples to study rheology effect of dispersant admixture? Absolutely, that would be a prime example of what you would want to do with this. You want to look the effect of the admixture, how it works on one and the other mix, when they have the same flow. You could absolutely put this in the rheometer, and you would get very quick and visual conclusions of which of these admixtures works best for your purpose. It would work very well.
Okay, so we're right at 5 o'clock. We will continue to stay online if you've got questions. And but other than that, I want to thank you for your attendance. And as I mentioned, we'll be sending out links to the recorded session as well as the slides. So I want to appreciate your attendance today, and have a great evening.